Alright, so today I'm going to go over classifying chemical reactions, which is chapter 7 in your textbook. Now, what you want to do is you're looking for pattern recognition, and that's something not only in chemistry, but in all science and in all nature you do. You simply look for the pattern and then you apply the pattern over and over again. Now, if you download the note sheet that goes along with classifying chemical reactions, you can see that I've already set up the different patterns for you. So today I'm just going to go through and highlight some of these different patterns that you would see. Alright, so the different types of reactions that we're going to be looking at are single replacement reactions, in which one thing replaces another, double replacement reactions, in which two cations exchange with each other. Your book, I believe, calls it an anion exchange. Acid-base neutralization, which your last Smart Sparrow lab will be involving, is kind of a special case of a double replacement reaction. Synthesis, that's where you have two elements or compounds that combine together to make one, so you're synthesizing it. Decomposition, it's the opposite of synthesis. You start with one thing and you get two or more products out. It sounds just like, this time of year, it's nice and hot out, when there's a, roadkill raccoon or possum or deer, and you can tell because you can smell the decomposition. You start with one big thing and it decomposes into two or more other things. Combustion reaction. And the most common kind of combustion reaction is going to be the burning of a hydrocarbon. So all fossil fuels are hydrocarbons, but you have burning with oxygen, and oxygen is in all the products. I would take a look at the giant flaming gummy bear video. There's an excellent example of a combustion reaction. And then your book talks about oxidation reduction reactions, which are called redox reactions. We're not going to worry too much about redox reactions. If you take second semester general chem, you'll get into redox reactions. So first of all, a single replacement reaction. A single replacement reaction usually involves a metal with another metal ion that is dissolved in a solution. So you have a solid and you have an aqueous, and the solid metal will replace the one that is aqueous. So there's an example of a single replacement reaction. And so it looks like we have some copper nitrate that is in there with another metal, and you can see the red stuff is actually the copper ion. Chances are that that solution then probably, I'd have to take a look at the activity series and see, but it looks like iron that it's on there. So, and you can also see that the solution is going from that bluish green color to clear, indicating that the copper ion is coming out and becoming the solid, these pieces that are growing there. So looking at it generically, we have A plus BC yields B plus AC. So here's your solid metal. Here's the solid metal after it then. So the solid metal dissolves or reacts with the other aqueous metal. It precipitates out. And using the activity series, we can determine whether or not a reaction will occur. There is the activity series. Now, something that is up here will replace something below it. And so I know that was copper, so we have to have something more active than copper. And let's see if iron is listed on here. I don't see it, so possibly it could have been zinc. That was zinc and copper nitrate. The copper precipitated out and zinc became zinc nitrate. A double replacement reaction. Double replacement, just like it sounds, two things change places. So you have two aqueous solutions or mix consisting of cations and anions, and what will happen is they bump into each other and then they precipitate out as an insoluble precipitate. Your solubility rules is what you would use in order to figure out with these ones whether or not a reaction is going to occur or not. So generically, we have AB plus CD yields AD plus CB. So A is going to come over, take the place of C. C comes over, takes the place of A. And then we would look at our solubility rules, which are uploaded under supplementary materials on Google Classroom. also known as a cation exchange or an anion exchange or a precipitation reaction, sometimes also called double displacement. All the ions in a double replacement reaction are going to retain their same charge. So if you have lead 2 on the left, it's going to be lead 2 on the right. It's not going to be lead 2 on the left and lead 4 on the right. And so there's a little graphic indicating a double replacement reaction or double displacement. Here we have Mario and Luigi, and at first they are paired up, and then what happens during the reaction is they switch. And again, you'll use the solubility rules to determine if a reaction will occur in the identity of the precipitate, which there's several tables of them in your textbook as well. Acid-base neutralization is a special subset of the double replacement in which you have an acid reacting with a base. When you react an acid with a base, you always get water and a salt as the product. So H2O, and what remains, the salt is the cation from the base, and the anion from the acid is what is called a salt. So sodium chloride is not the only salt. There are hundreds, if not thousands, of salts. So for instance, magnesium hydroxide, commonly known as milk of magnesia, and hydrochloric acid, stomach acid. So you take milk of magnesia to help when you have excess stomach acid. And what will happen then is you get magnesium chloride, which is actually going to be aqueous. Just like salt water, if it was sodium chloride water, magnesium chloride is going to be aqueous, plus water is your product then. Almost always the salt is going to be soluble in water. There are a couple of cases, exceptions to that, where the salt is insoluble, but the majority of the time the salt will be soluble in water. You evaporate the water and then you're left with the salt. Ding, 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 here you go. Here's another bonus extra credit opportunity. For those of you that are watching the videos, I have an article, another Chem Matters article on vanilla. And when we go through empirical formulas in the next chapter, in chapter 8, this is one of the compounds that we'll be finding the empirical formula of. So if you're watching this video, email me at brian_leonard@ivcc.edu. and I will send you a copy of the Vanilla Chem Matters article and also some questions to answer about the article. Send it in to me and you'll get up to 10 points extra credit. The acid reacts with a base to make two neutral, hence the name neutralization, pH equals 7.00 on the pH scale, 7 is neutral, compounds. And there's a little graphic of it in which the HCl comes in, reacts with the sodium hydroxide. They exchange their cations and we get water and then sodium chloride as the product. And this is all 1-to-1 ratio, so it's now a balanced equation. So quickly the pH scale then. Below pH 7 is acidic, greater than pH 7 is alkaline or basic. This is a logarithmic scale. So if you go from pH 6 to pH 5, it's not 1 times more acid, it's 10 times more acid. If you go from pH 6 here to pH 4, that would be 10 squared, so that's 100 times more acidic. A 6 to a 3 would be 1,000 times more acidic. Technically, and again, we do not need to do this for our class, it's beyond the scope of our course, but the pH is equal to the negative logarithm of the hydrogen ion concentration. So the reason that it's called pH, it's the power or exponent of hydrogen. Now, normal body pH of your blood is between 7.35 and 7.45. Outside of that range, your cells do not function properly. If it's below pH 7, you get acidosis, which is not good. And if it goes above that, it's alkalosis. So those are both things that you would need to be treated for in a hospital. A synthesis reaction is when you have two reactants and one product. So you got A plus B yields AB. Again, look for the pattern recognition. You have two reactants, you got one product. So a good example of that is the Haber process for producing ammonia. And a huge amount of the energy used by the entire Earth in a year, something like 8%, I believe, of all the energy is for the Haber process. It also produces a lot of carbon dioxide. So they're trying to find a better way of producing ammonia, because this is where all the fertilizer comes from for farming. So here we have N2 plus 3H2 yields 2NH3. So here we have the nitrogen over on this side, we have the hydrogen over on this side, and using a catalyst, which is something that speeds up a reaction but itself is not used up, it produces the ammonia. Decomposition reactions, one reactant becomes two or more products. AB yields A plus B, so it decomposes. So again, there's the pattern. If you have one reactant, look to see if you have two or more products. Chances are you have a decomposition reaction. And there's a little animated decomposition. We start with AB, and it goes to A plus B. Really fun reaction, and this one of those YouTube people did not too long ago. They used gallons and gallons of hydrogen peroxide and potassium iodide, but it's called elephant toothpaste. And that is simply some dish soap added into there with 30% hydrogen peroxide and potassium iodide as the catalyst, so it speeds up the decomposition and making a whole bunch of bubbles. Notice he doesn't have his safety goggles on, so that's a big no-no. Make sure, especially with that one, that you had safety goggles on. Combustion reactions, again, combustion is when something burns. Oxygen is a reactant and appears in all the products. So easy way to identify this then, you have A plus O2, because oxygen is a diatomic. One of those diatomics always has its charges 2- in compounds, except in peroxides. Like in the last one we saw, hydrogen peroxide is H2O2. A to the X, O to the Y. So this is your first element there, whatever it happens to be. Oxygen, and the X and the Y represent the subscripts. And again, often A is going to be a hydrocarbon. When a hydrocarbon burns in excess oxygen, carbon dioxide and water are the products. That's why in the winter time you can see the water vapor coming out of the tailpipe of a car, truck, whatever the case may be, because it generates a large amount of water. And you can see as it condenses from water vapor back into liquid water, the condensation coming out of the tailpipe of the car. In the summertime, you don't notice that because it doesn't lose the energy. It doesn't convert from a gas being back into a liquid again. But the water is definitely there. So the internal combustion engine would be a good example of that. Gasoline plus oxygen yields carbon dioxide, water, and a whole lot of fire and heat. And that's what drives the piston down. And so here we have the intake. Piston comes up, fires the spark plug, you get the explosion. Exhaust valve opens up then, forces the exhaust out. And then when it comes back down, because it's driving it down here from this counterweight on the crank, so that way it keeps going around, it draws in a new fuel-air mixture. This is the catalytic converter, which is designed to get rid of the nitrogen oxides primarily out of your exhaust and makes it cleaner then. And then we have down here, there's a lot of water vapor that's coming out there along with the other byproducts of it, carbon dioxide, carbon monoxide. Now, redox reactions. All batteries are redox reactions. It involves the transfer of electrons. And again, it's mentioned in your book, balancing redox reactions is completely different than the balancing reactions that we have done. And this is why sodium and the halogens are a perfect fit, or for that matter, the alkali metals and any halogen, because sodium has one extra valence electron, outer electron. If it can get rid of it, then it has the same number of electrons, or isoelectric, as neon does. Same thing with fluorine. Fluorine has 7 valence electrons. It wants 8 like neon does. So the sodium will donate its electron to the fluorine. So sodium and fluorine is a perfect match because of that. After the electron has been transferred, then you have the electrostatic interaction between the positive sodium ion and the negative fluoride ion, helping hold that crystal together. But it's not before that electron has taken place, that transfer has taken place. Alright, so I have uploaded a worksheet on Google Classroom to go over or identify the different types of reactions. Make sure that you read Chapter 7 as well. And then I will add some more problems. The ones from the book, most of them include redox reactions, which we're not really going to worry as much about. But we are going to take a look at single replacement, double replacement, acid-base neutralization. So just look on Google Classroom and I'll update that.